Hello students, good day all. In this session, we are going to learn the continuation of kinetic theory of gases. This kinetic interpretation of the temperature, Maxwell distribution function, the law of equipartition of the energy, which is specific heat capacity, and the mean free path. One by one, let us see elaborately, children. Yes, students. The relation between the pressure and the kinetic energy per unit volume. Now, the pressure which is exerted by a gas of density which has the rho and the RMS velocity is V, which I have taken, means the P which is equal to 1 by 3 rho V square. Then the mass per unit volume of the gas which is equal to volume into density, as we know that this formula, it's a basic formula, that is, so 1 into rho which is equal to rho will come. Then the average kinetic energy of the translation per unit volume of the gas which is equal to E dash. It's equal to half rho V square. So P by E dash, then we have taken this P by E dash in this way. We will get that value of 2 by 3 by simplified this equation. So P which is equal to 2 by 3 times of E dash. So that this E dash, so the average kinetic energy per unit volume. Now the pressure from this thing we have, we can say that the pressure which is exerted by a gas which is equal to the 2/3 of the average kinetic energy of the translation per unit volume of the gas. Yes. Maxwell's distribution of molecular speeds. See, we can say in any gas, the molecules which are randomly that colloid, right? If suppose it is getting randomly colloid against with each other, so that the velocity of any individual gas molecules will get changed continuously. So, because of that, the speed which getting varied in any instant, the speed of the molecules which varying over a wider range. Here, we have to say the velocities which are a distribution that remains fixed in any that steady state. So, the graph which we are going to draw, the graph of NV versus the velocity. That is, we can say that is the Maxwellian speed distribution curve, right? There is a Maxwellian speed distribution curve that shows that the molecular speed, how it is getting varied. So this we have taken in that x-axis, that is for V, right? Now the curve, the distribution curve will be, suppose in this way it is getting varied, then the value that here in that x-axis we have taken the speed, right? And here we have taken the number of molecules that is moving with the speed. How it is moving with the speed. So this is both we have taken. So now see the distribution. I have taken this particular part that as a shaded part, maybe getting varied, dV, the change, a small change in that speed here. So here I have taken this, which is for the V, it is a real curve, and this part I have taken that way. So here the shaded part, the characteristics or the important features from this graph we have taken means, if suppose at any temperature, the speed of the molecules will vary from 0 to infinite. It will be any variation will shows through that. And the second point, you may see the shaded part. This will give the number of molecules. That means the velocity which maybe lies between V and dV. Got it, children? Yes, the degrees of freedom of a monatomic gas. Now we are going to see for the degrees of freedom of monatomic, diatomic and the triatomic gas. One by one, let us see. The monatomic gas, that we can say that the molecule of the monatomic gas, like a helium, neon, like that we have taken, means it actually consists of the single atom. So it is capable of the translatory motion only. So the motion is translatory. So we have taken here the value n, which is equal to 1, then the k, which is equal to 0, because it has the translatory motion, so that the f, which is equal to 3 into 1, so minus 0, that is equal to 3. So the freedom, the degrees of freedom here for the monatomic gas is 3. The same way, if we have discussed for the degrees of freedom of a diatomic gas, then for the diatomic gas, the molecule of diatomic, that is O2, N2, these and all we have taken. If suppose, you can see the diagram, children. By the diagrammatical way, we can explain the A and B. These are the two atoms which is separated at a distance we kept, right? So, here the gas, it's corresponding to the translatory motion, we can say it has 3 degrees of freedom for the translatory motion. But the total number of freedom, we are saying here 5. Because of it has a rational motion too. So that we can write here n, which is equal to 2, and k, then here 1. So f value, we can say that f, which is equal to 3 into 2 minus 1. So the 6 minus 1 is 5. So the here degrees of freedom 5, right? By that only for the diatomic, the degrees of freedom, which is 5, right? Right. So degrees of freedom of a triatomic gas. So it has actually the 2 types. One is non-linear molecules, another one is a linear molecule. Non-linear molecules, which we have taken, means the molecules which are all at the vertices. So it is located at the vertices. So maybe you have taken a water molecule or SO2, like these and all will be at this. So how the value of the degrees of freedom is the triatomic molecules, for that 3 value it will be come for the translatory motion, and the another 3 number it will be come for the rotational motion, and another 3 it will be go through the center of mass. Then the n, which is equal to 3, then k value is also 3. Then what it will be f, the degrees of freedom f, which is equal to 3 into 3, then minus 3. So you will get 6. So the degrees of freedom for the non-linear molecule is 6. Versus we have taken for the linear molecule. Same here you have taken that the triatomic values of the molecules. It will be arranged actually in the straight line. Maybe you can take CO2 or HCN or any type of the molecules of the triatomic. It will be arranged in straight line. So that the independent relation for this will be 2. Then F, the degrees of freedom F, which is equal to 3n minus k. Then it will be 3 into the 3 minus the k value which we have taken here, the independent relation is 2. Then the value, the F value which is equal to, then we will get 7. Right. So this is for the linear molecules. Right. The specific heat of monatomic gas. See, the monatomic gases, if you have taken like a helium, argon, so these and all is 3 translational degree, right? So according to law of equipartition of energy, if you have taken, means the average energy which is associated with each degrees of freedom per molecule, which is equal to 1/2 kBT. See, average energy which is associated with each degrees of freedom per molecule, we can say that is equal to 3/2 kBT. So the total internal energy of 1 mole of the molecular gas or a monatomic gas. So here U, the total internal energy, U represented by U, which is equal to 3 by 2 kBT into Na. So which is equal to, by simplified we will get 3 by 2 RT. Right. Now you need to know about the molar specific heat at a constant volume and the constant pressure. So here for the constant volume, that is a d by dt of U. So d by dt of that U, we will get 3 by 2 R. Right. Now here Cp, that is the constant pressure. For the constant pressure, we can say that Cp monatomic, that is Cv plus R. So the Cv value, which is equal to 3 by 2 by R plus R we can take, means 5 by 2 R. So the ratio gamma, which is equal to Cp by Cv, only we have to get the specific heats of monatomic gas. So that is equal to 1.67 we will get. So the specific heat of solids. So near at room temperature, the molar specific heat of the most of the solids at the constant volume, which is equal to 3R or 6 calorie mole per minus 1 Kelvin per minus 1 or 25 joule mole per minus 1 Kelvin per minus 1. This will prove that is energy, that is kinetic energy Ek, which is equal to, we can say 3 into 1 by 2 kBT. Right. So which is equal to 3 by 2 kBT. Right. Now here EP, which is equal to, that is 3 into 1 by 2 kBT, which is equal to 3 by 2 kBT. Or we can write for the total value, which is Ek plus EP, which is equal to 3 kBT, right? Now U, which is equal to Na into 3 kBT. So that this will become 3 RT. Now the value which is for the dull, the change in the value Q, which is equal to dull V plus P into dull V, which is approximately, this will be equal to the change in the volume. So here the constant volume Cv, which is equal to dull Q by dull T, which is equal to dull V by dull T. So that is equal to 3R. So this value will be proved, the constant volume, which is equal to 3R. Right. Specific heat of water. Here the water, like we can say, we may treat the water which is like a solid by the law of equipartition of the energy. The average vibration energy per atom is 3 kBT. Right. Now a water molecule, that we know that it has 3 atoms, 2 hydrogen atom, 1 oxygen atom. Right. Now the average vibrational energy per water molecule is what? 3 atoms. So the 3 into 3 kBT, so 9 kBT will come. Then the total value you need to know, right? So the total vibrational or the internal energy of 1 mole of water molecules is Na into 9 kBT. So this will come 9 RT. Now the change in the value, that is, we can neglect dull V. Like here, like we have taken in the solid. Here dull Q, which is equal to dull U plus P into dull V. So that it will be equivalent to that dull U value. So that constant volume, which is equal to dull Q by dull T, that is equal to dull V by dull T, is 9R. So that the value, the specific heat of water, which is here for 9R, right? Mean free path. See the mean free path, that means the molecule of a gas which are in the state of always continuous, rapid and the random motion. Okay. Now, we have taken as these molecules have a finite through a small size. So, they collide against one another frequently. So, the two successive collision, that means between the two successive collision, a molecule which moves along a straight line path with a uniform velocity, then we can call that as the path a free path. That means the mean free path. Now you are seeing the diagram. On the diagram, the velocities of each molecules which are getting changed both in magnitude and the direction. Hence, this each molecules which follows a series of straight line zigzag path. See, you may be seeing that as a lambda 1 is a molecule, maybe the magnitude is also varying, the direction is also getting varying with the other molecule. So this path we have taken for the molecule of a gas, right? Yes, students, so far we have learnt about the kinetic interpretation of the temperature, the Maxwell distribution function, the law of equipartition of energy, that is for monoatomic, diatomic and the triatomic gas molecules, specific heat capacity, how the specific heat capacity will become for the monatomic, the gas particle and the mean path, right? So this and all, so hope you people have understood. Thank you, children.